Okay, now we'll go to canonical transformations. So we'll discuss the theory today and also try to do a few problems. And I think the main type of problem that's being asked from here is to find whether a given transformation is canonical. So we'll see different methods, at least two of them, to find out whether a given transformation is canonical. Okay, we'll explain what we mean by a canonical transformation. So what we saw so far, right? We started with Lagrangian mechanics. We did the Hamiltonian formalism, okay, or Hamilton's formalism, Hamiltonian mechanics. Yet in we drew phase space diagrams, etc. We said that they have the same information, but this is this is in phase space, and this was in configuration space. Okay, and here we have 2n. So these are two Hamilton's equations are two first order differential equations. Right, whereas the Lagrange's equation is, our equations are one second order differential equation for each generalized coordinate. Okay, now still we have this idea of this Hamiltonian mechanism, especially when we wrote it in Poisson bracket. It looked like this, right? Qi dot is equal to Qi with h, Pi dot is equal to Pi with h. Okay. Now, still we have this idea, some of them are coordinates and some of them are momenta. Okay, when you hear momenta, you think about mass multiplied by velocity, etc. Okay, but we can still go make it more abstract. Okay, we can make it more abstract. Okay, making it abstract is good, all right, because sometimes when you go to higher physics, this conceptual ideas, physical ideas may sometimes not be useful. It may even stop you from thinking further. For example, when you go to quantum mechanics, it's better to have an abstract idea of this, all right, an abstract formalism for this. So when you go more abstract, we'll talk only, we don't have to talk about positions and momenta separately. Okay, we'll put, okay, already the positions and momenta, coordinates and momenta, all right, coordinates. Okay, so the basic idea of the Hamiltonian approach is to put the coordinates and momenta in almost an equal footing. Right? We don't really separate between coordinates and momenta. So we said phase space is 2 n-dimensional n coordinates and n momenta. Now we'll speak of just a 2 n-dimensional space. That's all. 2 n-dimensional space and 2 n coordinates. Okay, 2 n coordinates include coordinates and momenta in this form, but you don't have to think of momenta as mass multiplied by velocity or something. These are just coordinates of some abstract space. All right, now this view will be helpful later on. Okay. All right, so we'll transform between, so far we might have seen coordinate transformations like this. All right, a new coordinate Qi prime is a function of old coordinates and time, maybe Pi prime of Pi comma t. Such transformations we might have seen, but now we are going to transform between all these 2 n coordinates. All right, and then we talk about certain class of transformations called canonical transformations. So that's the basic idea. Right? Now this might be especially useful. All right, this canonical transformations may be especially useful because we talked about cyclic coordinates. Cyclic coordinates. If a certain coordinate does not appear in the Hamiltonian, there is a momentum, there is a conserved quantity. Right? But in a given coordinate system, this cyclic coordinates may not be obvious. Right? You have to make a good coordinate transformation where the coordinates are cyclic. Right? Now, if you are not limited, if you can transform between coordinates and momenta, we'll be easily able to find coordinate transformations, not coordinate transformations, transformations. Okay, transformations where, for example, all the momenta are cyclic. Okay, all the momenta are cyclic. Oh, sorry, all the coordinates are cyclic. Then all the momenta will be constants, and it's easy to solve the problem. Okay, so this certain freedom in this transformation will be very helpful later on. All right. Okay. So these transformations, we can think of such transformations. Qi is equal to Qi of Q comma T. All right. These are the new coordinates and these are the old coordinates. Okay. Now these are called point transformations. Point transformations in, let's say, configuration space. Okay. So the idea is that, okay, the idea is that we have in configuration space or Lagrangian mechanics, we have n generalized coordinates, right? We can take some other combination. We can make some coordinate transformation and find a new coordinate, right, in coordinate space, right? So the new coordinate will be the function of the old coordinates. So rotation is an example for a point transformation. Okay, so the new coordinate is a function of old coordinates, and then we say that we have a point transformation in configuration space. Okay. Now we generalize this concept. We generalize this concept to define what we call as point transformations in phase space. Okay, in phase space. Now, what do we mean by that? Here we mean that we'll have Qi is equal to Qi of Q comma P comma T. So we are putting these positions, coordinates and momenta in equal footing. So the new coordinates will be a function of new old coordinates and momenta. All right, these are just like coordinates of phase space. Coordinates of phase space, all right, and you will have the new momenta as functions of old coordinates and momenta. And there may be a time, but most cases that we discussed, we won't have a explicit time dependence. Okay, this is the general thing. Now the new coordinates are functions of not only the old coordinates, but also of the old momenta. Also new momenta are not functions of just the coordinates, but it's also functions of old old coordinates, all right? Not only functions of old momenta, but also functions of old coordinates, all right? So this distinction between momentum and coordinate, it's not very clear now, okay? So now it's the coordinates and momenta are still on an equal footing. It's not exactly on an equal footing. There's a small asymmetry because, as we said, we know that Qi dot is equal to dou H by dou Pi, whereas Pi dot equal to minus dou H by dou Qi. It's not completely symmetric. Okay, so such kind of asymmetry should be present here also, right? So that's the, so this is not, we cannot think of all transformations. We are thinking of specific transformations in such a way that they do behave like coordinates and momenta. Okay, they have to, this new coordinates and momenta have to behave like coordinates and momenta. What do we mean by that? Okay, all right. So let's say that we are interested in only those transformations for which Q and P are canonical coordinates. Okay, what do you mean by canonical coordinates? All right, that's not very clear, but the idea is that what was the important thing about this Qi and Pi? The important thing is that there exists a function h, all right, in the phase space. There exists a function of the coordinates and momenta in such a way that the evolution of the system is given by this equation. All right, or there exists a function h. Okay, so if you look closely at it, the defining property is that there exists a function h such that, all right, let's write it in Poisson bracket, Qi dot equal to Qi with h and pi dot equal to pi with h. All right. So this function has to be there. Right? Now in our we cannot think of any random transformation. We should have, even if you make a transformation, we should have some function, all right, which determines the evolution of the system by exactly these equations. All right. So this means that there must exist a function. This is the definition of the, this is the definition of the canonical transformation, what we call as the canonical transformation. All right. Now we can find equivalent definitions for that, or we can start from different definitions, but let's start from here. Right. So the idea that if this transformation, such transformation has to be canonical, there must exist a function, let's say k of q comma p, all right, such that the equations of motion, or the time evolution equations, right, for the new set have the form, right? It should exactly, so there should be some function, we call it k, okay, so we can call it h prime, so it should be like this, such that qi dot is equal to dou k by dou pi, and pi dot is equal to minus dou k by dou qi. Okay. Now, if there exists such a function which gives you the evolution of the coordinates and momentum, new coordinates and momenta, according to exactly these equations, okay, then we say that our transformation is a canonical transformation. Okay. So we are talking about a class of transformations. We are talking about a class of transformations which evolve according to the Hamilton's equations of motion. All right. Okay. Is that clear?
Yes.
Okay.
Yes.
So this new function k, it plays the role of a Hamiltonian. In the new coordinate system, but in the new coordinate set. Now we don't talk about coordinates and momenta separately, we just call them all coordinates. Okay. These are all coordinates of phase space. Okay. Role of Hamiltonian in the new coordinate set. Okay. This can be called as the transformed Hamiltonian. Okay, sometimes people jokingly call it also as the Hamiltonian, because if H stands for Hamiltonian, then K might stand for Hamiltonian, all right? Now we can try to, now let's find if this has to be satisfied, all right? Now, how do we find the transformation equations, right? We need to find the transformation equations between the new set and the old set in such a way that such a condition is satisfied. Now, how do we do this? How do we do this? All right. Now we know that this condition, all right, integral L dt is equal to 0, delta integral L dt. We said that the action has to be an extremum, right? Now, if for any physical path, this has to be correct. So we can use this condition in order to get to the correct transformation. So in the new coordinates or the old coordinates, this condition always will be satisfied for a physical system, path followed by a physical system. Am I right? We called it the principle of stationary action. Path followed by a physical system. So this should be 0. So we, between any 2 points, all right, this is basically taking 2 points in configuration space, taking all the possible paths between exactly the 2 points, and then you will see that the correct path will be one for which this delta, the first order variation of this functional, is 0. All right. So this means that we should have, okay, for the new coordinates and momenta, we should have this thing T1 to T2. We know that L can be written as Pi Qi dot, all right, minus H. Am I right? there's a summation implied, all right? I'm using Einstein summation convention. So there's a sum over I implied. We know that H equal to summation over I, Pi Qi dot minus L, all right? So this summation I don't write explicitly because it's a bit difficult to keep writing. So if it is repeated, if any two indices are repeated, you have to understand there's a summation. That's known as Einstein summation convention. So this has to be equal to 0. Okay. Now the old coordinates also satisfies the same condition. Am I right? Pi Qi dot minus. So there's a K here. Okay, I'm sorry. Am I right? The old coordinates also satisfy the same condition. All right. Now, okay, now we can also define the Lagrangian of the system. Okay, so I hope you are following. Okay, now we can define the Lagrangian of a system. Okay, we said that Lagrangian is T minus V, etc., but that's not completely correct. Right, only for some systems Lagrangian is T minus V. Right? Now, what's a good definition for Lagrangian? A good definition for Lagrangian is that a Lagrangian of a system, all right, is that function which obeys this equation, all right, which obeys the principle of stationary action for the correct physical path, all right. So what's the definition of a Lagrangian? Lagrangian should be that function which obeys this equation, okay, for the correct physical path, all right. Now this means that we are talking about the same system in different coordinates, right? We are talking about the same system in different coordinates, okay. And so this both have to be we are talking about the same system. So both of these have to be the Lagrangian. I'm sorry, I think I missed a dt here. Okay, dt. Right, there's no change in the time. It's a parameter of the system, right? We are not changing time in a coordinate transformation, right? Now, what does this mean? We are still talking about the same system. We are talking about the same system here in different coordinate systems. Same system. Okay. This means that both of these should be legitimate Lagrangians of our system. Right. This means that both of these, both the above must be, because by definition this is the Lagrangian. Right. If this condition is satisfied, then whatever is coming inside this, the integrand, is the Lagrangian. Okay. Both the above must be, let's say, legitimate Lagrangians. Does that mean they are equal? Does that mean they are equal? Okay. Does that mean they are equal? No, not necessarily. They could be equal. Okay, they could be equal, but there is some freedom in choosing a Lagrangian. If you remember, there is some freedom in choosing your Lagrangian. Am I right? We actually showed that. If L is a Lagrangian that gives you the equations of motion, okay, then we can say that L plus df by dt is also a Lagrangian, because it will give rise to exactly the same equations of motion, where f has to be a function of the coordinates and time, maybe. Okay. Now this transformation freedom is there. All right. That comes from the action principle. Okay. It can be easily shown from the action principle, but we showed in our previous classes that even if you change a Lagrangian by such a factor, all right, you will get exactly the same equations of motion. Okay. That's not all. You could also simply multiply your Lagrangian with a constant. Okay. You could also simply multiply your Lagrangian with a constant. Okay. And you get exactly the same equations of motion, because you are taking derivatives and setting it equal to 0. So this constant will go just there. All right. So this freedom is always there. So this means that these have to be related by this. This means that Pi Qi dot minus H has to be equal to, we can write it like this. Okay, this constant term I'll write here, lambda Pi Qi dot minus H. This is the Lagrangian. This is one possible Lagrangian. So this has to be equal to Pi Qi dot minus K plus a total derivative df by dt. All right. Now, this means that if your new coordinates have to be canonical, this condition has to be satisfied. All right. Now that lambda there is not very convenient. It messes with your Poisson brackets. Okay. So we'll just take lambda equal to 1. Okay, we'll just take the cases for lambda equal to 1. Now, even if you take lambda equal to 1, and if you want to deal with cases where lambda is not equal to 1, you could just find the case for lambda equal to 1, just multiply with whatever lambda you like. Okay, so we'll take cases with lambda equal to 1. Okay, you don't lose any generality. You can get the result. If you want to deal with some lambda is equal to 10 or something, right? You just find the canonical transformation for intermediate lambda where lambda prime is equal to 1. And then in the end, you can put lambda, then in the end, you can put lambda equal to 10. It doesn't matter. So if there is a transformation for lambda equal to 10, then automatically there is a transformation also for lambda equal to 1. Okay, so there is no problem there. Okay, so this means that we are talking about transformations of the kind. Okay. So we can say that by definition, this is our definition, the canonical coordinates must satisfy, or if your new coordinates are canonical, then this condition is satisfied. Pi Qi dot. Okay, I'll use small letters for the old coordinates and capital letters for the new coordinates. Okay. Okay, now, all right. So this we call as the canonical transformations. And if there is a lambda, we call it as extended canonical transformations. So if there is a lambda here, we'll call it as extended canonical transformations. This is the definition for canonical transformations. Okay. And we can also talk about restricted canonical transformations. Mostly we'll be dealing with restricted canonical transformations. Restricted canonical transformations means the transformation equations. Okay, Q will be Q of Q comma P comma Q comma P. There is no explicit time dependence, and capital P is equal to P of Q comma P. Okay, if there is no explicit time dependence, then we call them as the restricted canonical transformations, and we'll be dealing with restricted canonical transformation for most of it. Okay, all right. Now this choice of f, right? This choice of f. We have these transformations, right? We have Q as a function of Q comma P, this P as function of Q comma P. This function could be anything, right? It could be a function of Q comma P, it could be a function of Qi comma P, it could be any function, right? Now, if you are given a function of Q and P, capital Q and capital P, using the transformation function, transformation equations, you can make it function of Qi and Pi, no problem, all right? Or you can make a mixed function of small q and capital Q, all right? So it's convenient. It's convenient. This function is completely arbitrary. Okay, it just has to be a function of coordinates and momenta. All right, just needs to be a function of coordinates. It has to be a function of coordinates. All right, so it is convenient to. This cannot be a function of coordinates. It has to be a function of. It could be a function of old coordinates and new momenta. All right, in one coordinate system, it will be a function only of the coordinates. But you can use the transformation equations to make it a mixed function of coordinates and momenta. Okay? It's convenient to choose. It's convenient to choose f partly in terms of old set of variables partly in terms of the old set of variables and partly in terms of the new set. Okay, it is convenient to choose it in this way. All right. Now, in this case, we'll see that in this case, if you choose it as a mixed function, in this case, you can see that f acts as a bridge, between old set and the new set. Okay, so if you choose f as a function of mixed function of old coordinates and new coordinates, all right. When we say coordinates, we also mean momentum, so don't worry about that. All right, then if you choose f as a mixed function, then it acts as a bridge. We'll show that it acts as a bridge between old set and the new set, and we can call this f as the generating function. Okay, we can then call this f as the generating function of the canonical transformation. All right, then f can be called as the generating function of the canonical transformation. Okay, all right. So that's the basic idea. So I'll just summarize what we said so far. Right. So what we said so far is very simple. We said that we can talk of transformations like this: qi is equal to qi of qj comma, or simply q comma p comma t. Okay, new coordinates as functions of old coordinates and momentum. Pi is equal to pi of q comma p comma t. And we said that this transformation is called canonical if this condition is satisfied, right? Qi dot pi minus k, where k gives you the equations. Okay, q for q dot and p dot. Okay. Qi dot pi minus k is equal to qi dot pi or pi qi dot minus h plus df by dt. Right? Then we said that this function can be chosen as a mix using the transformation equations. Okay, we talked also about the restricted canonical transformations where time is not explicitly involved in the canonical transformations. All right. Now, yeah, we said about choosing f as a mixed function of old coordinates and new coordinates. All right, which means it could be momenta also. It could be functions of momenta also. Then f acts as a bridge between the old coordinates and new coordinates, and then we call it as the generating function. Okay, I hope this is clear. Okay, all right. This is all a bit abstract, but we'll see nice examples and then things will be clear. If you have any doubts, you can ask now. Okay, have you any doubts? Is it fine? Okay,
Fine, sir.
all right. Okay, so now I said that we need a mixed function, all right? Let's choose this. Suppose f is a function of, we call it as f1, okay? Capital Q and T generally. Okay? So these are the old coordinates, these are the new coordinates, and this is, so we have taken some old and some of them as new and function of T, all right? Now if this is the choice of your function, okay, I'll just do it for this. What's the condition that this transformation is canonical? The condition is that PIQI dot minus H is equal to, all right, PIQI dot minus K plus D F1 by dt. Right? You just demand this condition and you'll see that you can now find the old new coordinates in terms of the old coordinates. Okay, so when I say coordinates, I just remind you I'm meaning coordinates and momenta. Right, we are not going to separate between coordinate and momenta. Okay, all right. So now this you can write it as, this is PIQI dot minus K plus dF1 by dt. This is a function of Q, capital Q and T. All right, now this you can expand. This is equal to dou F1 by dou QI. All right, and you will have QI dot Okay, this is just chain rule. Okay, there is a summation over I here. There is a summation over I. You could also use K, doesn't matter. Plus dou F by dou Qi. Qi dot plus dou F by dou T. Okay, so what I've done here is that I'm expanding this total derivative. All right. So we know that this Q is a function of T and capital Q is a function of T. So the total time derivative involves. So when Q changes with time, how much does function F1 change? Okay, the change in function F1 when Q changes with time. Okay, that's this one. You take the derivative of F with Q and multiply it with Q dot. Okay, that's how you do it. Okay. Now the set Qi dot and capital Qi dot are separately independent. Okay, so you can take the coefficients of Qi dot and capital Qi dot and set them equal to separately set them equal. All right, you can collect all the coefficients of small Qi dot from the left hand side and equate it to all the coefficients of small Qi dot on the right hand side. Okay, similarly, you can collect all the coefficients of capital Qi dot on the right hand side and equate it to the collection of equated to the coefficients of capital Q dot on the left side. Okay, you just combine these terms and equate them separately. You see that you take the coefficients of Qi dot, right? You see that Pi, okay, Pi. Oh, there's no other Qi dot here. What Qi dot do we have here? Pi. It's just this, right? Pi is equal to dou F1 by dou Qi. That's all. Okay, we have collected all the Qi dots. Am I right? Yeah. So this condition has to be satisfied. Oh, wait. That's correct.
Dou F by dou T LHS.
That's correct, right? Yes, that's correct. Pi is equal to dou F1 by dou Qi. എന്താണ് പറഞ്ഞത്?
നമ്മളെ ട്രാൻസ്ഫോർമേഷൻ ഇപ്പം Qi ഡോട്ട് Pi മൈനസ് K ഈക്വൽ ടു Qi ഡോട്ട് Pi മൈനസ് H പ്ലസ് dou F by dou T
അല്ല df by dt ടോട്ടൽ ഡെറിവേറ്റീവ്. ഇത് df by dt ആണ്, ടോട്ടൽ ടൈം ഡെറിവേറ്റീവ് ആണ്. ഓക്കെ,
നമ്മൾ നേരത്തെ ഡിഫൈൻ ചെയ്തപ്പോൾ അത് ഇപ്പറേ അല്ലായിരുന്നു, LHS അല്ലായിരുന്നു ഡിഫൈൻ ചെയ്തിരുന്നത്. Qi ഡോട്ട്
ഇവിടെയാണ് എഴുതിയത്. അത് കുഴപ്പമില്ല, അത് എവിടെ എഴുതിയാലും കുഴപ്പമില്ല. റൈറ്റ്,
അതിന്റെ സൈനിന്റെ വ്യത്യാസം വരൂല അതോട്ട് പോകുമ്പം.
ഇല്ല, അങ്ങനെയാണ് നമ്മൾ കൺസിസ്റ്റന്റ് ആയിട്ട് ഇത് ഫോളോ ചെയ്താൽ മതി. എനിക്ക് തോന്നുന്നു ഇങ്ങനെ തന്നെ ഡിഫൈൻ ചെയ്തതെന്നാണ്. ഐ തിങ്ക് വി ഡിഫൈൻഡ് ഇറ്റ് ഇൻ ദിസ് വേ ഇറ്റ്സെൽഫ്. എന്റെ നോട്ട്സിൽ എന്തായാലും ഇങ്ങനെ എഴുതി. അതെങ്ങനെ എഴുതിയാലും വാസ്തവത്തിൽ എങ്ങനെ എഴുതിയാലും കുഴപ്പമില്ല, കാരണം ഇവിടെ ടോട്ടൽ ഡെറിവേറ്റീവ് ആഡ് ചെയ്താലും അവിടെ ടോട്ടൽ ഡെറിവേറ്റീവ് ആഡ് ചെയ്താലും കുഴപ്പമില്ല. Okay, it still would be invariant. It just have to be a total derivative of some function f of this form. Okay, so നമ്മളിപ്പോ ട്രാൻസ്ഫോർമേഷൻ ഇക്വേഷൻസ് ഇപ്പൊ ഇവിടെ ചെയ്താലും ഇറ്റ്സ് ദ സെയിം തിങ്, ഇറ്റ് ഡസന്റ് മാറ്റർ. ഓക്കെ, ഇനി ഇത് ഇങ്ങോട്ട് കൊണ്ടുവരികയാണെങ്കിൽ ഇറ്റ് വിൽ ബി മൈനസ് df1 by dt. പറഞ്ഞു ശരിയാണ്, പക്ഷെ ദാറ്റ് മൈനസ് f1 you can call it as some new function f3, doesn't matter. ഓക്കെ, ഇപ്പൊ നമ്മൾ ട്രാൻസ്ഫോർമേഷൻ ഇക്വേഷൻ ഡിറൈവ് ചെയ്യുന്നത് ഈ റിലേഷൻ ആണ്, അത്രേ ഉള്ളൂ. ഓക്കെ, ഫൈൻ. ഈ കണ്ടീഷൻ സാറ്റിസ്ഫൈ ചെയ്യുന്ന കനോനിക്കൽ ട്രാൻസ്ഫോർമേഷൻ ആണ് നമ്മൾ ട്രാൻസ്ഫോർമേഷൻ ഇക്വേഷൻ ഡിഫൈൻ. ഇനി ഇത് ഇങ്ങോട്ട് കൊണ്ടുവരികയാണെങ്കിൽ മൈനസ് f1 എന്നുള്ളതിന് നമുക്ക് പുതിയൊരു ഫംഗ്ഷൻ f ഇട്ടാൽ മതി, കുഴപ്പമില്ല. Okay, so it doesn't really matter. We'll do it like this because just to be consistent with what is given in the textbooks. Okay, similarly, you take the coefficients of Pi or coefficients of Qi dot. You see that there's a Qi dot here, capital Qi dot. You also have a capital Qi dot here. There's no capital Qi dot here. Am I right? Okay, you see that Pi plus dou f by dou Qi is equal to 0. This means that capital Pi has to be equal to minus dou f by dou Qi. All right, is this fine? Okay, we have got here
0 അല്ലല്ലോ 1 അല്ലേ വരിക അങ്ങനെ ഇക്വേറ്റ് ചെയ്യുമ്പോൾ?
അല്ല ക്യാപിറ്റൽ ക്യു ഐ ഡോട്ടിന്റെ ഫംഗ്ഷൻസ് കോഎഫിഷ്യൻസ് മുഴുവൻ എടുത്ത് ഇക്വേറ്റ് ചെയ്യാണ്. അപ്പോൾ നമ്മൾ കളക്ട് ചെയ്യാണ് ഇവിടെ ക്യാപിറ്റൽ ക്യു ഐ ഡോട്ട് ലെഫ്റ്റ് ഹാൻഡ് സൈഡിൽ ക്യാപിറ്റൽ ക്യു ഐ ഡോട്ടിന്റെ ഫംഗ്ഷൻ ഒന്നുമില്ല. ദർ ഇസ് നോ ഫംഗ്ഷൻ ഓഫ് ക്യാപിറ്റൽ ക്യു ഐ ഡോട്ട്, റൈറ്റ്? ദർ ഇസ് നോ കോഎഫിഷ്യന്റ്, ഐ ആം സോറി, ദർ ഇസ് നോ കോഎഫിഷ്യന്റ് ഓഫ് ക്യാപിറ്റൽ ക്യു ഐ ഡോട്ട് on the left sides, right?
Okay.
So the coefficient of capital Q I dot on the left is 0. On the right it is Pi plus dou F by dou Qi. Okay?
Okay. അവിടെ ഇൻ ബിറ്റ്വീൻ ദ ടേം ഒന്നും എടുക്കുന്നില്ലല്ലോ.
ഏതാണ്
അത്? അത് മൂന്നാമത്തെ സ്റ്റെപ്പിലേക്ക് മാറ്റില്ലേ? ഓക്കെ. അല്ല ഇവിടെ അണ്ടർലൈൻ ചെയ്തിട്ടുണ്ടല്ലോ.
അതെ,
ഇവിടെ
ഇത്
PI QI ഡോട്ട് മൈനസ് എച്ച് എന്ന് പറഞ്ഞിട്ട് അണ്ടർലൈൻ ചെയ്തിട്ടുണ്ടല്ലോ.
അതെ,
ഈ ലെഫ്റ്റ് ഹാൻഡ് സൈഡിലുള്ളത് ഈ ഫൈനൽ സ്റ്റെപ്പ് ഒന്നും അല്ല ഇക്വേറ്റ് ചെയ്യണത്.
അതെ ഇതിനെ എക്സ്പാൻഡ് ചെയ്തതാണല്ലോ.
ഓക്കെ.
അത് ഞാൻ അണ്ടർലൈൻ ചെയ്ത് തെറ്റിപ്പോ, സോറി. ഓക്കെ, ഇതുമായിട്ടാണ് ഇക്വേറ്റ് ചെയ്തത്. ഓക്കെ, സിമിലർലി യു സീ ദാറ്റ് there is what is left, you have got h here, right? And whatever is left have to be equal, right? So you've got k here and dou f by dou t over there. So you see that k has to be equal to, okay, take k to the other side and bring h to this side. H plus dou f by dou t. All right. Now this equations, it's easy to remember. I'll give you a trick to remember this. Okay, so these are important. These are the, now you can obtain the transformation equations. We are interested in the transformation equations. Okay, so if you know this function, you can just write this equation and then invert it to find the correct transformation equations, right? Now this is a function of q, capital Q and t, am I right? Okay, now you construct this equation, you know this relation. Okay, then you can invert this equation to find capital Q in terms of small q and small p. Okay, similarly you can use this thing to invert it to find capital P in terms of small q and small p, etc. All right, so these relations sufficiently describe or sufficiently define the transformation. So we can find the transformation equations from this, and f1 here is known as the generating function of type 1. So that it's a function of small q, capital Q and t. We have take half of the coordinates from the old coordinates and half of the coordinates from the new coordinates, and then define the generating function. Okay.
ഇപ്പൊ നമ്മൾ ഒരു സംശയം ചോദിക്കട്ടെ?
ചോദിക്കും.
ഇപ്പൊ ഫംഗ്ഷൻ നമ്മള് Q ക്യാപിറ്റൽ Q T എന്നല്ലേ അതിന്റെ വേരിയബിൾ ആയിട്ട് എടുത്തിട്ടുള്ളത്?
അതെ.
അത് നമ്മള് Q P T എന്ന് എടുത്തു കഴിഞ്ഞാൽ വീണ്ടും അടുത്ത ട്രാൻസ്ഫോർമേഷൻ ഇക്വേഷൻ കിട്ടും. അപ്പൊ അതേമാതിരി കിട്ടും. അങ്ങനെ 4 ടൈപ്പ് ട്രാൻസ്ഫോർമേഷൻ ഇക്വേഷൻസ് നമ്മൾ പരിചയപ്പെടുന്നുണ്ട്. പക്ഷെ ആക്ച്വലി ഇൻഫിനിറ്റ് ടൈപ്പ് ഉണ്ട്. ഓക്കെ, ഇത് നമുക്ക് ഏത് മിക്സ്ചർ വേണമെങ്കിലും എടുക്കാം. ഇൻഫിനിറ്റ് ഇല്ല. ഓക്കെ, ഡിപ്പെൻഡ്സ് ഓൺ ദ നമ്പർ ഓഫ് കോർഡിനേറ്റ്സ്. ഇഫ് യു ഹാവ് ഫൈനൈറ്റ് നമ്പർ ഓഫ് കോർഡിനേറ്റ്സ് യു ഹാവ് ഫൈൻ. ബട്ട് ഇതിപ്പോ നമ്മൾ ചെയ്തിരിക്കുന്നത് പകുതി കോർഡിനേറ്റ്സും പകുതി ഓൾഡ് കോർഡിനേറ്റ്സും പകുതി പുതിയ കോർഡിനേറ്റ്സും എടുത്തു അല്ലേ? ഓക്കെ, ഇവിടെ നിന്ന് ഒരെണ്ണം ബാക്കിയെല്ലാം അപ്പുറത്തുനിന്ന് എടുക്കാം. അങ്ങനെ ഏത് കോമ്പിനേഷൻ വേണമെങ്കിലും എടുക്കാം. റൈറ്റ്? അതല്ല, ഇനിയിപ്പോ നമ്മള് അടുത്ത കിട്ടാൻ എടുക്കുന്നത് സ്മോൾ പി ക്യാപിറ്റൽ പി ടി ആണോ അതോ QPT ആണോ?
അത് നോക്കണം. അത് ഒരു ടൈപ്പ് 1 എന്ന് പറഞ്ഞ് ഇതാണ് ഡിഫൈൻ ചെയ്യുന്നത്. ടൈപ്പ് 2 ഐ തിങ്ക് വിൽ ടേക്ക് സ്മോൾ q ക്യാപിറ്റൽ P and T, I think. Okay, we'll see. Right? But the important thing is the functional dependence, and I'll tell you with an easy way to remember these equations. Okay, ബാക്കി എല്ലാത്തിനും നമ്മൾ ഇതായിട്ട് ചെയ്യേണ്ട ആവശ്യമില്ല. It's the same method we'll be doing for different kinds of functions. Okay, for the others I'll just give you the equations, and I'll also tell you a way to remember it. Right? So the basic idea is that you can invert this to find capital Q as a function of P and Q, and this you can invert. All right, you can put Pi equal to minus dou f1 by dou Q. You can invert this and find, okay, you can invert this and find this is basically Q, capital Q and T. Right, so you can find capital
capital Pi equal to, ഇപ്പോൾ മൂന്നാമത്തെ ഇക്വേഷൻ കിട്ടിയത് capital Pi equal to minus
dou f1 by dou Qi.
ഏത് കോഎഫിഷ്യന്റ് ആയിരുന്നു ഇക്വേറ്റ് ചെയ്തത്?
Qi ഡോട്ടിന്റെ ക്യാപിറ്റൽ Qi ഡോട്ടിന്റെ ഇതും
അതല്ല, നമ്മൾ അതിന് മുമ്പും ചെയ്തത് 0 എന്ന് ഇക്വേറ്റ് ചെയ്ത് ഇപ്പുറത്തെ സൈഡില്
ഇതല്ലേ? അതെ, അത് തന്നെ. അതിനെ ജസ്റ്റ് മാറ്റി എഴുതിയെന്നേ ഉള്ളൂ.
ഓക്കെ.
Pi equal to minus dou f1 by dou Q എന്ന് മാറ്റി എഴുതുന്നേ ഉള്ളൂ. Okay, all right. So that's all. That all looks good. It's fine. Okay. Now, in principle, we can find the transformation equations from here. That's all. Okay. You may be asked to find the transformation equations, or you may be asked to find the generating function. Okay. So given the appropriate generating function, you can find the transformation equations. Also, if you are given a transformation equations, first you can integrate this. All right, you can integrate this equation and find the generating function also. Okay? For simple problems, you may be asked like that. But then there's a problem of there's some freedom of the integration constant, etc. But in principle, you can do that. Okay. Now let's look at type 2. Let's look at type 2. We can choose your function as f2 of q comma capital P comma t. Right. So we have taken half of the old coordinates and half are the new momenta. Right. So this is a function of n old coordinates and n new momenta. Right. Now for this, the relation, you do exactly the same thing, and in the end you get pi. Pi is equal to dou f2 by dou qi, and that's exactly the same, right? It's dou f1 by dou qi here, it's dou f2 by dou q here, and you'll see that here you have a capital P, so what you get is qi is equal to minus, so it's also dou, not minus, dou f2 by dou pi, okay, and k is equal to h plus dou f2 by, okay. In fact, we can start from f1 and make a Legendre transformation to get f2, if you're familiar with Legendre transformations. Okay. All right. Now, this is not exactly how it's defined in Goldstein, but this will suffice. All right. You remember that there is some function of q capital P and t. Okay. Now, we'll talk about the other kind of generating function. F3. We can, എന്താണ്
സെയിം ഇക്വേഷനിലോട്ട് കൊടുത്തു കഴിഞ്ഞാൽ അങ്ങനെ ചെയ്തെടുക്കാൻ പറ്റുമോ നമുക്ക്?
നമ്മൾ ചെയ്ത അതേ സ്റ്റെപ്സ് ഫോളോ ചെയ്താൽ മതി. അവിടെ ഡോട്ട് ടേമിന്റെ കോഎഫിഷ്യൻസ് ഇക്വേറ്റ് ചെയ്താൽ മതി. ഇവിടെ നമ്മൾ ക്യു ഐ ഡോട്ടിന്റെ ഏത് ഈ സ്ഥലത്ത് നമ്മൾ പി ഐ ഡോട്ടിന്റെ ചെയ്യേണ്ടി വരും. ഓക്കെ, ഇറ്റ്സ് എക്സാക്ട്ലി ദ സെയിം സ്റ്റെപ്പ്.
Yes, sir. Okay, okay.
Now f3 we write it as function of p, q and t. Okay, f3 as a function of p, q and t, and in this case you do exactly the same thing. Equate the coefficients of the dot terms and you'll get this thing. You see that q is equal to minus dou f3 by dou p, okay, and p is equal to dou minus dou f3 by dou q, and for k it's exactly the same. I didn't write it here because it's k equal to h plus dou f by dou t. It's the same. I think I should write it. K is equal to h plus dou f2 by dou t. Here we'll have k is equal to h plus dou f3 by dou t. Okay. All right. I think I should write an index also, qi, pi. Okay, okay. Now there's one more type. So what we did so far is, I'll explain, all right? What we did so far is, we are trying different kinds of functions, all right? Here, f1 is a function of q1, sorry, small q, capital Q and t. What's f2 function of? It's small q, capital P and t. Right? If it are old new coordinates, new moment, right? And f3 is a function of, we again start from here, instead of small q here, we take the old momentum, small p, capital Q and t. So what's left? What's left? We can have small p, capital P and t. Am I right? Okay, I'll write it here. We have got F4. Okay, you can actually think of any combinations of this type. It doesn't matter. These are the general F4 of small p, capital P and T. Right. In this case, you'll get Qi is equal to dou F4 by dou Pi. Okay. And there's a minus. Right. And you'll see capital Qi is equal to dou F4 by dou Pi. Okay, and that's it. The rest is the same thing. H is equal to K plus dou F4 by. Okay. Right. So these are the four different types of generating functions that we can talk about. Okay. Now I'll give you an easy way to remember this. Okay, let's we need some way to remember this, all right, because it can be asked directly or you may need to use it in an equation, all right. Some function might be given and you need to immediately, you cannot derive all this, all right. You need to immediately know what the transformation equations are, okay. Oh, yeah, what's the relation between old and new coordinates are in terms of the generating function. Now you can see that there is some nice pattern here. What was the first function, right? First function was f is equal to, we say, let's just say f1, generating function f1. Okay, so we have got f1 of what was it? Q, capital Q and T. Right, we take half as the small old coordinates and half as the new coordinates. Okay, yeah, all right. Now it's easy to remember that. You take this function, this position as 1 inside the bracket, all right? This as 2, a function as 1 and 2. Okay? In the first place, you will always have the old one. In the second place, you will always have the new one. All right, you always write the given generating function, you always write it in terms of first you write the old one and second you write the new one and third the time. Time doesn't matter. Okay. Now you remember one more thing. Q is always in the first position, all right? The first position is always reserved for Q, and it's not exactly like that. You just remember like that. Okay. And if Q is in the first position, then there is no minus sign. Okay. And if P is in the second position, there is no minus sign. If it's interchanged, then there is a minus sign. So in this case, let's see. So here you've got small q, right? Small q. So you can say P is equal to dou F1 by dou Q. The small p is always related to a small q. All right, small p is always related to the small q, and here q is in the first position, so there is no minus sign, it's a plus sign. Okay, now for the second one, you see that capital P is equal to dou F1 by dou Q. All right, so capital P and capital Q are always related. Okay, but here q is in the second position, so there is an extra minus sign. Right? So if q is in the first position or p is in the second position, don't put any minus sign, it's all plus. But if q is in the second position, you put a minus sign, or if p is in the first position, you give a minus sign. Okay, that's easy to remember, isn't it? Yeah, did you get the trick?
Yes,
is it
sir.
okay?
Okay, fine.
Let me just check if I'm right here. Yes. Okay. Pi, so you write it like this. Pi is equal to dou F1 by dou Qi. Capital Pi equal to minus dou F1 by dou Q. This is correct. Okay. And for this thing, it's always the same. K equal to H plus dou F1 by dou T. Okay. Now you can think of the second type. Okay. For the second type, it is F2 of, instead of the small q, we take a P. Am I right? So you don't have to remember which is F1 and which is F2. You'll be given a function in a program. All right. Then you can just, so this is F2 of old coordinates P and new coordinates. You don't change this. Okay. Change one at a time. Right. In this case, you see that there's P in the first position. All right. If P is in the first position, you get a minus sign. So Qi is equal to minus. Okay. Qi is always dou F by dou Pi, small pi. So this is F2. Okay. Now P is in the first position here, which we don't like. We give a minus. All right. So it's some kind of symmetry is going on there. Now for you have got Q here. So what we get is capital Pi. This is equal to dou F2 by dou Qi. But Q is in the second position here. So it gets also minus sign. Right? If Q is not in the first position, you give it a minus sign. Is this fine? So in
Yes,
the
sir.
same way, you can do it for all. Oh, I think I made a mistake. I think F2 was, we defined F2 as a function of, sorry, okay, F2 was not this, F2 is this. F2 we defined as a function. Instead of this capital Q, take the capital P, that's all. So this is Q, P and T, that's F2, right? That's the F2 that we gave, I'm sorry. Okay, you don't have to remember this number. This is just classification, right? But here again, so initially you take old coordinates, new coordinates and time. Then you keep the old coordinates, you change it to this new momentum, old coordinates, new momentum and time. Okay? So in this case, again, it's easy to see. Pi is equal to dou F2 by dou Qi. Q is in the first position, no minus sign. Okay. What about capital Qi? We have got a P here. Okay, so what we get by taking derivative is capital Q, dou F2 by dou Pi. Okay, here P is in the second position, so there is no minus sign. Okay, and again, K is equal to H plus dou F2 by dou T. Okay. Now, what about the third case? In the third case, what was our F3? F3 we took it as F3 of, here is where we take, yeah, instead of this we take P, Q and T. Okay, it was F3. Now it's easy to write down. As we said, we have got a P there. So what we get is Qi. Qi is equal to dou F3 by dou Pi. But P is coming in the first position here. So it gets a minus sign. Okay, this is a consistent way to remember it. And you see that this is what we have here is capital Q. So what we get by differentiation is capital P, right? If it's capital Q, you get capital P. If it's small q, you get small p. If it's small p, you get small q. If it's, yeah, like that. Okay. So Pi is equal to, this we can write as Q is in the second position. So it gets a minus sign. Dou F3 by dou Qi. Okay, all right, that's correct. Both gets a minus sign. Okay, and again, K is equal to H plus dou F3 by dou T. Okay, so that's easy to remember. Now, what was our F4? What was our F4? In place of F4, we had small p, capital P, and T. Am I right? Yes. Okay, so you see that Qi, what you have is small p here. So what you get by differentiating is small q. Okay. Qi is equal to dou F4 by dou P. Is there a minus sign? Is there a minus sign? Should there be a minus sign?
Yes, yes.
Yes, good. Okay. And what about the next one? Capital Qi is equal to dou F4 by dou Pi. Should there be a minus sign?
No.
No, very good. All right, so this is easy to remember. Now you may not be given the number exactly. It's easy to remember anyway. You start with Q, Qt and change one each. And these things are, all these things are connected by Legendre transformations, but there are generating functions which are not connected by Legendre transformation also. Okay, but all these four can be obtained by taking consecutive Legendre transformation from the first function, just like we get the thermodynamic potentials. All right. Okay. So yeah, now you may be given, we'll see some examples, all right? You may be given some generating function and you need to find the old coordinates and new coordinates, okay? Constructing this equation may not be sufficient. You also may have to invert it, but we'll see some examples, okay? All right. And also we need to check whether a given transformation is canonical. I'll just jump ahead and give you this result, okay? So we said that we can axiomatically right, obtain all of classical mechanics by the Poisson bracket relations. Okay, so obviously, if we are talking about any real mechanics here, the fundamental Poisson bracket relations must be the same. Okay, it has to be the same, right? So, I mean, we want to prove it, but it's always true that the fundamental Poisson brackets are invariant under canonical transformations. Okay, not fundamental Poisson brackets. Any Poisson brackets are invariant under this thing, canonical transformations. All right, this is just a result we'll use. Okay, we know that Qi with Pi. We don't have to write the subscript because it's invariant. Qi with Pj will be delta Ij. Okay, we'll also see that Qi with Qj is equal to 0, just like the Pi with Pj will be 0. Okay, also we'll say that if you take two functions u and v, okay, whether you take it the Poisson bracket in terms of the old coordinates and momenta or the new coordinates are momenta, you'll get exactly the same. It's not very difficult to remember. Okay, so we won't be explicitly proving this. This comes from the fact that this also has exactly the same Hamiltonian structure, right? Instead of h, you have a k, that's all. So the whole thing, the Poisson bracket thing will work. Okay, it has to work. Right? In other words, you can define canonical transformation. Right? You can now construct a new definition for canonical transformation. You can define canonical transformations as those transformations which leave the Poisson bracket relations invariant. Okay, so canonical transformations are those transformations of coordinates and momenta which leave the Poisson bracket relations invariant. Right, you get exactly the same Poisson bracket relations. That's one way of defining canonical transformations. So there are problems where there is another method. There are a few methods to check whether a given transformation is canonical. We'll be just looking into two methods, and that should be sufficient to solve all the problems. Okay, either you check the Poisson bracket, it always works. Sometimes the Poisson bracket finding the relation may be a bit difficult, but it always works. Okay, there's another condition that we will discuss in the next class. Okay, thank you. If you have any doubts, you can ask now.
Clear, sir. Thank you.